In this lesson, we're going to look at graphing equations. In particular, we're going to cover graphing linear equations. Now let's first of all recall what the Cartesian plane is. So the Cartesian plane is used to specify pairs of numbers like this, a comma b, graphically on a plane, as we see below here. So this is what we call the Cartesian plane. Notice that we have an x-axis, that's the real number line, and then what we call the vertical one is the y-axis, that's another number line, so they're placed perpendicular to each other, and we can graphically represent an ordered pairing of points like a comma b right here as a dot somewhere on this plane. So the A is called the x-coordinate, and notice that if we drop down perpendicularly to the x-axis, right there is the number A on the x-axis. And if we move over horizontally to the y-axis, right there is our number B on the y-axis, and this is A down here on the x-axis. Write them a little larger so you can see it. And so that's how we graphically represent points on the Cartesian plane. For example, if we wanted to represent the point 5, 2, the 5 is our x-coordinate and the 2 is our y-coordinate. And so we would go over to 5 on the x-axis, move up until we hit 2 coming across, and right about there would be the point 5, 2 on the Cartesian plane, that point right there. If you wanted to represent the point -3, -2, the -3 you'd move over on the x-axis to -3, and then you'd move down to -2 on the y-axis, and right about there would be the point -3, -2. Alright, so that's what we call the Cartesian plane, and that's how we represent points graphically on the Cartesian plane. Now let's consider an equation like y equals 3x plus 2. Now notice if we put x equaling 1, if we put 1 in for x, we get back 5 for y, right? 3 times 1 plus 2 is 5. Now we can represent this particular solution. That's a solution to this equation. If I put 1 in for x, I get 5 back for y. We can represent that as an ordered pair, 1, 5, and we can graph that on the Cartesian plane. Now also notice that 2, 8 is a solution. If I put 2 in for x, I get 6 plus 2, that's 8. And if we put 0 in for x, we get back 2 for y. So these are also solutions to this equation. Now if we plot all of these solutions, every possible solution to this equation on the Cartesian plane, we obtain what we call the graph of this equation. And we can find the graph by creating a table like we have down here, and then plotting each of these points on the Cartesian plane, and then connecting the dots with a smooth curve. So you notice we have this table down here. If x is -2, y is going to be -4. Notice 3 times -2 is -6, plus 2 is -4. If we put -1 in for x, we get -3 plus 2, that's -1, and so on. 0 in for x, 2 back for y, and so on. And so here are the ordered pairings listed over here. Now what we can do is we can plot all of these points on the Cartesian plane, and as I mentioned, just connect them with a smooth curve. Now if you go into Moodle, there is a website that's listed called Geogebra. You can click on it and you'll come up with a website that looks like this. Just grab that Cartesian plane. Notice you have the Cartesian plane right here in this window pane. You can just grab it and move it around. And we can graph these functions and points on the Cartesian plane. So let's see, we wanted to graph, just put it over here, we wanted to graph y equals 3x plus 2. And let's recall what some of those points were. We had like if x was 0, y was 2, so we can plot that point over here. So 0, 2 would be right there. If x is 1, y is going to be 5. So we can plot that point right here. And we had if x was 2, y is going to be 8. That's another point. And that's actually up here, right there, just going off screen. And negative 1, we'll just plot one more here. Negative 1, negative 1 was another solution, and that is right here. And then you just need to connect these with a line. Well, it's going to be a line, is actually what it is. And that's roughly what our graph is going to look like. It's a little difficult for me to draw using this stylus, a straight line, but that's exactly what it is. And using GeoGebra, we can actually precisely graph this equation. If you move over here, you can input the equation y equals 3 times x plus 2. You don't have to put the times in between the 3 and the x, the times symbol. It's fine with that. Let me make that font a little larger so you can see it. Alright, there we go. So there we entered 3x plus 2, and over here you'll see the actual line 3x plus 2 appears, this black line right there. So that's the actual graph. So let me erase the one that I drew by hand. So here's the actual line. This is the graph of y equals 3x plus 2. So that's what the graph of this equation looks like. So every point on this graph represents a solution to this equation. For example, if you look down here, negative 2, negative 4, right there is a point that is a solution to this equation. If we put negative 2 in for x, we get back negative 6 plus 2, that is negative 4, which is on the y-axis. Now let's notice a few things about this graph that are important to take note of. First of all, notice this is called our y-intercept right there, that point right there on the y-axis. Notice that is the point where x is equal to 0 and y is equal to 2. That's where the graph crosses the y-axis, so that is called our y-intercept. That point right there. Now notice for linear equations like this one right here, notice how our y-intercept appears right there. Well, that's not a coincidence. Anytime you write an equation like y equals mx plus b, this is a linear equation. That is always going to be your y-intercept. So the b is your y-intercept. And that's your y-intercept because if we put 0 in for x, notice we get back b for y. Also, let's take note what the slope of this line is. Now the slope, let's take note of this. If we're sitting anywhere on the graph, like let's say we're sitting right here, we have a point right here. If we move over 1 unit to the right, notice that to get back onto the graph, we have to move 1, 2, 3 units upward to get back on the graph. So we have this little triangle here. This distance is 1, and the rise is 3. So we say our run is 1 and our rise is 3. That's what we call the slope of this line. So the slope equals the rise over the run. And in this case, it is equal to 3 over 1, or just 3. Now that number tells you how steeply the line is leaning, or how close to vertical it is. The larger your slope, the more vertical your line is going to be, because if you go over 1 unit and your slope is a large number, you're going to have to go up pretty far to get back onto your graph, and hence your line is going to be very vertical. Now notice for linear equations over here, like mx plus b, or for our particular equation, notice that right here, that 3 right there, that is our slope. That's not a coincidence. So this is our slope. And any time you have an equation, a linear equation like y equals mx plus b, the m is always going to be your slope. And so we call this form, this y equals mx plus b form, we call that the slope-intercept form for the equation of a line. Because we have our slope, that's the m, and our y-intercept is the b. So that's called our slope-intercept form. Now let's note one other thing graphically here. Just note, if the slope were a negative number, how would that change my graph over here? For example, if we were to change that 3 right there to a negative 3, how would that change our graph? Well, let's think about this for a second before we actually hit enter. What it would do, oops, I hit enter accidentally. Well, what it does is, if you go, you still have your y-intercept of 2 right here. That's still your y-intercept. So right there you are on the graph. If you move over 1 unit to the right, well, now you, because of the negative, you have to move down 3 units to get back on your graph again. So 1, 2, 3 units down. So that's negative 3, and this is 1. So notice now your line leans in the other direction. So before, our line was leaning, as we went from left to right, it was leaning upward. Now it's leaning in a downward fashion as we move from left to right. And that's because our slope is a negative number now. So lines with positive slope will lean in that direction. Lines with a negative slope will lean in that direction. Okay, so that's something to keep in mind as well. And if we were to make that negative 3 a larger number, the line would become more vertical. Notice if we made this negative 3 up here, let's make it a negative 6. And now if we hit enter, and there we go, we see our line is more vertical now. Notice how if we go over 1 unit now, we have to go down 6 units, 1, 2, 3, 4, 5, 6, to get back on the graph. So this distance right here would be negative 6 now. Alright, so that's a quick introduction to graphing equations of lines. You can also use this to graph other equations as well. If you want to explore that, you can even graph quadratics like x squared. Right there, that's called a parabola right here. So right here would be the graph of y equals x squared. Notice in particular, if I take a point like letting x equal 2, if we let x equal 2, we get back 4 for y, right? If I put 2 in here, 2 squared is 4. And if I put negative 2 in for x, we also get back positive 4 for y as well. So there are 2 points on the graph. And this is called a parabola. So you can explore other graphs as well. Keep in mind you can also graph equations on the TI-83 if you have that calculator available. You can graph functions on the TI-83. For example, let's graph that 3x plus 2 equation. If you click the y equals button right here, and then you just type in 3, you'll see a whole list of functions that you can put in. You can graph multiple functions on the TI-83. So we'll type in 3. Now the X button is right here. You see there's an XT theta N button. 3x plus 2. And then let's just click on that zoom button right there, and we'll pick number 6 for our standard viewing window. And there's the graph of 3x plus 2. And you can even trace along it if you hit the trace button. It puts a little cursor right there, x is 0, y is 2, and you can move along the curve using the left and right arrow buttons. So you see, like right now, x is approximately 2, well, it's about 2.1, y is 8.4 approximately. Alright, so that's how you can graph equations with the TI-83. And this here, this is all just mentioning what we've already talked about previously about our Y-intercept, the slope of a line. Y equals mx plus b is called our slope-intercept form, and this down here is just discussing how the line, how vertical a line appears is dependent on that number m right there. So I'll let you read through that. Now here are a few examples. Let's take a look at these. If you want to try these on your own, feel free to pause the video here. So let's sketch the graph of these 3 functions. Let's first do 2x minus 5, then we'll do 3 halves x plus 3, and negative 3x plus 4. And then we'll do this one. So the first one, 2x plus 5, let's go back to Geogebra. Delete that one. I'm going to zoom in a little bit. You can zoom in using the mouse wheel. So for 2x minus 5, alright, so our y-intercept is negative 5, so that would put us down here. And our slope is 2, so if we go over 1, we will have to go back up 2 to get to another point on the graph. So there we go, there's another point on the graph. And we could even plot a few more. If we go over 1, we'd go up another 2, over 1, up another 2, and so on. And so then we can just sketch the equation of our line would be very roughly like this, and so on. A little difficult for me to draw with the stylus on the computer screen. Let's graph it in GeoGebra, or you can use a TI as well. And so we'll have 2x minus 5, and yep, right there. And here's the graph of our function y equals 2x minus 5. Right there. Let's graph the other one. What was that? That was 3/2 x plus 3. So let's graph that one. Let's delete this one. All right, now the y-intercept here is 3. So right there is 3 on the y-axis. The slope is 3/2. Now what that means is if we go over 2 units, 1, 2, we will have to go up 3 units. So I'm going to have to move this Cartesian plane down here a little bit. So let's see, right there is where we were. Right, now 3/2, the 3 is the rise, and the 2 is the run. So if we go over 1, 2, we will have to go up 1, 2, 3. Right there's another point on the graph. And then we can just connect them with a straight line. And that is very roughly what our graph would look like. Like I said, it's a little difficult for me to draw. Let's actually have Geogebra graph it here. So 3/2 x, y equals 3/2 x. By the way, when you have a fraction like that, if you want to move out of the denominator, hit the right arrow button. Plus 3. And yep, there's our graph. Not too bad. Our blue graph that we had sketched is right on top of that one. So right here we see the graph of, that's the graph of y equals 3/2 x plus 3. Right there. And let's graph our final one. And that was -3x plus 4. Alright, so for this one, our y-intercept is 4. Let's delete this graph up here. So our y-intercept is 4 right there. Now, the slope is -3. So if we go over 1, we'll have to move down 3 units. 1, 2, 3. Right there's another point on the graph. And if we go over 1 and down another 3, 1, 2, 3, there is going to be another point on the graph. And so we'll connect these with a straight line. And that very roughly is the graph of this function. Let's have Geogebra do it for us. So if we type in y equals -3x plus 4, right there, well, my graph was off a little bit over here. Should have gone up like that. And so right here we see the graph of -3x plus 4. And that's the graph of our equation. Let's take a look at the final problem. Let's place this equation, 2x plus 3 minus 5 equals 0, into slope-intercept form and sketch the graph. Alright, so we want to take this equation and we want to get y on one side and all of our x's on the other side and put it into slope-intercept form. So we have to move the 2x and the -5 over to the other side. So let's do that. So if we start out with now to move the 5 over to the other side, we can move this -5 over, but then it will become +5, right? That's the same as adding 5 to both sides. So we'll have 2x plus 3 equals 3y equals 5. Now we want to move the 2x over. Well, when we do that, it will become negative 2x over here. That's the same as subtracting 2x. And we end up with 3y equals negative 2x plus 5. And now we have to divide by 3. Divide everything, each side, by 3. And we get y equals... Now I'm going to split this up by our properties for fractions, our distributive property. Remember, we can split this up as negative 2/3 x plus 5/3, like that. And so down here we will end up with and there we have it. We are finished. That's the equation of our line, and that is in slope-intercept form. So the y-intercept is 5/3 and our slope is negative 2/3. So let's graph that. So let's go over here to Geogebra. We just have to remember what that is. So we're going to graph negative 2/3 x plus 5/3. So let's sketch that by hand. Now for the y-intercept, 5/3, that's 1.67. Check that out on a calculator if you like. 1.67 is approximately right here on the y-axis, so that's a point on the graph. Let's also delete this old graph that we have here. Now our slope is negative 2/3. So remember, this is going to be our rise divided by our run. So what this means is if we move to the right 3 units, 1, 2, 3, we will have to move down 2 units because of the negative. So I'll move down 2. 1, 2. So that's about negative 0.3 right there on the y-axis. Moving down 1, 2 units there. And then I just have to connect this with a straight line. And so that very roughly is going to be what the graph of our line looks like. And let's check it out with Geogebra if we were to graph it. Let's check our answer here. So we would just type in y equals negative 2/3 x, remember to move out of the denominator, plus 5/3. And there's our graph. Yeah, pretty close. Oops. Alright, so the black line right here, that's our graph of our function y equals negative 2/3 x plus 5/3. And there you go. So that concludes this lesson on graphing linear equations.